Okay, so now that we've proved the discrete ground wall lemma, we're in a position to talk about convergence. So the basic idea behind convergence is the following. So a method is convergent, okay, if the limit as h goes to 0, right, where h is b minus a over the number of steps n, right, and you look at the maximum pointwise error for k equals to 0 all the way up to n of the difference between the numerical solution y sub k and the exact solution y at tk. All right. So what's happening here is the following, right? So for a given time step, where h is b minus a over n, so you have n plus 1 points, right? Where n0 is, where t0 is just the initial time. You look at the difference between the numerical solution and the exact solution for all of those points, and you look at the maximum of that. So you look at the maximum pointwise error, and then you ask yourself what happens to this quantity as h goes to 0, or equivalently as n goes to infinity. And you want this to be equal to 0. So basically the idea is that as you take smaller and smaller time steps, you want the pointwise error you're making, right, by replacing the exact solution with this sort of approximation of the numerical solution at approximation of the continuous solution at a bunch of points. You want that the maximum error of that goes to 0. Okay, so that's a very, very natural notion of error and of convergence. So with that in mind, the claim is the following. So the theorem is that the Euler method is convergent. Well, okay, so let's try to prove that. So the way you prove this is to first start with your Taylor theorem. So Taylor's theorem, or Taylor theorem. Okay, it says that y at tk plus 1 is equal to y at tk plus h f at t k y at tk plus something which is big O of h squared. All right, and you compare it to yk plus 1 is equal to yk plus hf tk yk, which is the Euler method, okay, exact solution Euler method. Okay, so then you can look at the error, ek plus 1 is the difference of these two things, okay, right, so ek plus 1, okay, so the difference of this is the error at the k plus 1 stage. This difference is the error at the k stage, so ek plus 1 is equal to ek plus h, okay, so there's a difference between the two vector fields, f at tk y tk minus f at tk yk. All right, and then you have something which is big O of h squared. Okay, so we're taking the difference of these two equations and defining that to be the error at the k plus first stage. All right, so now we can take absolute values and use the triangle inequality, and I'm going to replace this term here by ch squared. All right, so this tells me that the absolute value of the error at the k plus first stage is less than equal to the absolute error at the k stage, right, plus h times the absolute error of this, the absolute value of this, right, okay, plus ch squared. Okay, so again, this is the function f evaluated at two different values of y, but the point is that the difference between this value and this value of y is exactly the error at the k stage, right? So we're again going to use the Lipschitz estimate for this. Okay, so this is less than equal to the absolute value of ek plus h times L, the absolute value of the difference, right? Right, but this term here is ek, right, plus ch squared. Okay, so this is just the error at the first k plus first stage is equal to the error at the k stage plus h times L, the error at the k stage, plus ch squared. Okay, so this is of course equal to 1 plus hl, absolute value of the error at the k stage, plus ch squared. So now it's like you have an inequality which is satisfied by the error, which then looks exactly like this recurrence inequality we had for the discrete Gronwall lemma, right? So the error, the k plus first stage is some multiple, the error at the k stage plus some additional term, which is of course the local truncation error term. Okay, so you can then use this to apply the discrete Gronwall lemma. Okay, so let me write down this. ek plus 1, absolute value less than equal to 1 plus hl, error at the ek stage, plus ch squared. Okay. All right. So okay. So now you apply the discrete Gronwall lemma. Okay, which says that the error at the k stage is less than equal to ch squared over alpha minus 1, alpha to the k minus 1, alpha to the k, error at the 0th step, okay, where alpha is this multiplicative factor. Alpha is equal to 1 plus h times L. Okay, so this second term vanishes because E0 is equal to 0. So you assume it's like with the Euler method that at the initial time, it's like you use y0 is equal to y at t0 for the Euler method. So in particular, E0 is 0, right? Okay, so that term vanishes. So you're just left with this term here. Okay. So this is less than equal, well, actually this is equal to, okay. So alpha minus 1 is just h times L. So ch squared divided by h times L is ch over L. Okay, and then 1 plus hl to the kth power minus 1, right? So that's what it is. Okay, so there's one additional observation, which is that because hl is greater than 0, right, 1 plus hl is going to be bounded from above by e to the h times L, okay? And you can see this by just the series expansion for e to the hl. It's like it includes 1 plus hl as the leading two terms. It's like, and then all the other terms are positive. So clearly this bounds this term here. Okay, so that's an observation. Okay. So as a consequence of that, right, I can bound this term here by e to the, I can bound 1 plus hl, it's like by e to the hl. So I can bound 1 plus hl to the kth power by e to the khl, okay? So this is absolute value of e to the k is less than equal to ch over L, all right? And then e to the hl times k minus 1. Okay, but you know that h is equal to b over a, b minus a over n. Okay, so h times n right? So h times n is equal to b minus a, and then k is less than equal to n. So this is less than equal to ch over L, right? E to the L times b minus a. Okay, so this implies that h times n is equal to b minus a, but k is less than or equal to n. So so hk is less than or equal to b minus a, right? So that's basically what's happening. We're taking the h and the k and replacing it with the b minus a from above. Okay, minus 1. Okay, so that's the term which we have. And you can easily convince yourself that well, this is just a constant, right? And then these are also constant. So the only thing is that this is big O of h, basically, right? So this is big O of h. So from this you can conclude, right? We can conclude that the limit as h goes to 0 of the error is equal to 0. And this is true for all k. It's like so that means that the Euler method is convergent, right? And actually, you know, it's like we actually established a uniform bound on the error. It's like everywhere, right? So the error, it's like along the entire trajectory is bounded by this term here, right? And then that scales like big O of h. So as h goes to 0, that goes to 0. So and as a consequence of that, the Euler method is convergent. All right, so that's basically what we wanted to show. And again, it's a relatively straightforward application of this discrete Grunwald lemma. So let me just stop here.